Very good afternoon. Today we are in the hydrology class again. We have 1 hour class from 4 to 5. We are still in the CO2, analyze the frequency and probability of the hydrological data. For those students not speaking, can you mute your mic? First thing, maybe please do remember to sign in your attendance, because this is very important to appear in your system and it will be counted during the for the examinations. We will count your attendance. It's sometimes if you are not sign the attendance, it will be quite complicated, so very difficult to add on the things. So please see the high scanning is that. I received some question regarding some more information on infiltrations. I think that's very good. The students start to studying on the works. If you are interested on the learning more on the infiltrations in our syllabus, you can find this book. So, Engineering Hydrology. In the chapter 3.15 infiltrations. So infiltrations here, you can get more information, particular for the Horton's methods. You will find in the subsection of the 3.18.1 Horton equations 1933. For this one, maybe we can give a closer look on that. Sometimes you'll find that some of the hydrological work we study depends on a lot of graph drawing, maybe like probability and the manual calculations. Hydrology is a very traditions discipline. Maybe it's quite new for you to learn the terms of hydrology. But the modern hydrology, what we say, like for the modern hydrology, before this we also using the water resources. Since like we have civilizations more than 5,000 years, we keep using the water resources, and we deal with the river, we deal with the rain for the agriculture. So it has been have a long investigations. For the modern hydrology, those method for the measurements is being proposed a few hundred years ago, and for some of the equations like the Horton equations we share in the last lectures, maybe it's proposed like Horton's 1933 is close to 100 years ago. So that's why at the time it's still not yet have the computer. If you understand the years of the proposal of the theory, then you will know why at the times like they use a lot of graph, a lot of probability. But it's very good. You can keep looking on that, because according to our syllabus, we have 2 textbooks, and most of the thing is from that. And this is another textbook. You can see the hydrology and floodplain analysis. This book is a book by a US author. You will find that from the experts from different places that have different approach as well. So for the frequency analysis for this book is in chapter 3. So there's two information sharing. Before we go to today's class, we continue on our PPT, which is uploaded in the Weibo. You can get the information. You can get the information from that. So now we continue on the frequency of rainfall. In many hydraulic applications, such as those concerned with the flood probability and occurrence, particular extreme rainfall, a 24-hour maximum rainfall will be of importance. The frequency analysis of the point rainfall data. Historically, we have used the rain gauge to do the measurements like previously we have discussed. Malaysia have about 1,500 from DID, Department of Irrigation and Drainage, to measure the rainwater. So we have large amount of the data, hydrological data. We need to do the analysis. What we more concerned is, we are more concerned on the storm, which is that got the how frequent the heavy rain is occur in our catchment area, and this is very important for us in the design of the drainage system. So you can see we have shared this one yesterday, T equal to 1 divided by P. This is the fundamental of entire concept of the hydrological analysis, or maybe we call it frequency analysis. The rainfall is random according to the understanding of the hydrology. We don't know today will rain or maybe tomorrow will rain. You can try to imagine previously they bring in the probability or maybe frequency analysis to analyze whether the coming days will raining or not. Now it will be better because we have the better system and we have the superpower computer. We can do the meteorological study to do the weather forecast. But previously, traditionally, we have set up a quite complete rain station network in order to measure the rain. And this hydrological data is very useful for the frequency analysis. T, also known as ARI, this one we talked yesterday. I believe most of the students is quite new for the hydrology, particularly on the frequency analysis for the hydrological data. So it's no harm like sir repeat on this concept. So for the CO2, frequency analysis is mostly we try to focus in most of the country. Can say almost all the country, including like in Middle East, in Africa, in US, in Europe, in China, in India, or in Malaysia, or the entire Southeast Asia. We are recording the rainfall using the rain gauge. Previously, sir has shared the equipment how to measure the rain. Therefore, we have accumulated a large amount of the data, and we are using the historical data in the design of our drainage system. The method we are using, you always heard about return period or average recurrence interval. T is known as return period, or maybe is 1 divided by the probability. If the 100 years return periods t equal to 100. That means like the p equal to 1%, 0.01. Every year it will happen the 100 years rainfall is only got 1%. This thing Sir shared yesterday already. Just try to enhance the entire things and how to do the probability calculations, and you can look into that, and in more detail you can get from the book as well. So this one Sir has been sharing yesterday, and today maybe like Sir will share another example. Like this is plotting the positions when we have one rain gauge station at a specific point. We want to plot the data for maybe 30 years or 40 years data. The purpose of the frequency analysis of an annual series is to obtain the relation between the magnitude of the event. Event is mean hydrological events here, and its probability of existence. The probability analysis may be made either by empirical or by analytical method. A simple empirical technique is to arrange the given annual extreme series in descending order of magnitude and to assign an order number n. Thus, the first entry m equal to 1, for the second entry m equal to 2, and so on, till the last event for which m equal to n equal to number of years of record. The probability of p of an event equal to or existed is given by the Wilbur equations. P equal to m divided by n plus 1. P is the probability. M is the n is the total sample. M is the which sample. The recurrence equal to t equal to 1 divided by p. You can see this one. Actually, this for the formula. Normally, we use the Wilbur equation. This is the well accepted we use, but it has other scientists they propose different method like the Hazen, California, Chico Davis, Brom, Green Gordons. You can see from these examples, like let's say we have a station A. We recorded the data for 22 years, from 1960 up to 1981. Now we want to do the frequency analysis for this data. You can see like if we have a stations, normally we measure the annual rainfall. So from 1960, we have the annual rainfall 130 cm. 1961, we have 84 cm of the rainfall, lower than the previous year, and 76 for the years 1962, and lower than previous 2 years. And the rainfall increased to 89. After that, increased to 112. 65 is keep reduced again, and 66 reduced again. 67 increased to 125. 68 increased to 143, and you can see like for this 22 years of the data, this 169 is year 1969 is 28 cm. So don't be confused. In Malaysia, normally we use mm, and in US they like to use cm. Even compared to the rainfall, average rainfall in Malaysia is about 2,000 mm. You can see like their rainfall is about 1,300 mm, is still less rain compared to the tropical country like Malaysia. So you can see they try to do the frequency analysis on this data. The first thing they want to estimate the annual rainfall with return period of 10 years and 50 years. What we can do on this data is we need to rearrange the data and then do the plotting. From the plotting, we can make the estimations on that. So at the first thing you can see, we try to rearrange of the data. M1 equal to 1 with the ascending, so the highest at the top. M1 equal to 160 cm, M2 equal to 143, and M3 equal to 130. And you can see the ascendings, the highest from the top. After that, the 22 is the lowest, 60. We use the Wilbur equations to calculate the probability. For the chances of with the rainfall equal or more than 160 cm, we do the calculation. M, this one equal to 1. If your hands, you got the calculator, or maybe you got handphones, you can try on that. So you can see like M equal to 1 and N plus 1 equal to 23. And this one, the N equal to 22. You plus 1 become 23, and 1 equal to M. 1 divided by 23 equal to 0.043. You got the probability P, and you try to calculate the return period T equal to 1 with P, then 1 divided by 0.043. You got about 23 years of the return periods. What does that mean? It means like it will only happen once in 23 years according to the probability analysis. So for the second rainfall 143, you use the formula again. So this one M equal to 2, and it seems still 22 plus 1, 23. Probability you will get 0.087. You got the P already, then T equal to 1 divided by P. You got 11.5 return periods. Actually, it's quite makes sense, is it? You got the 22 years data, and in your 22 years data, got 1 times is the data at 160 mm. So the return period is 22. So the second highest you got the return period is 11.5 year will happens again according to the probability. So for the third one, you can see you use the same method. M equal to 3 and 22 plus 1, and you got the P equal to 0.130, and T you use equal to 1 divided by probability, you got 7.667. So you do all these use the Wilbur equations to get all this probability, then you can get your data for the return periods. A graph is plotted between the annual rainfall magnitude as the ordinance and return period as the logarithmic scale. Normally, we will plot with the return period with the logarithmic scale. Arithmetic scale is the common scale. You can see after you do all these calculations for 22 years. Let you see again just now the data. So this one you got the data you got in the station 1960. You get the rainfall. And 61, you get the second rainfall, you do the measurements, all these measurements. You got the data for 22 years up to 1981. So what normally, if you are the civil engineer, you got this data, what you normally do is you need to calculate the return periods. So you got a sample of n sample of 22 years. You need to calculate. You need to arrange the ascendings on that. Use the Weibo probability to get the probability analysis. Then you calculate the return period. After that, if you understand that this work is being proposed like before, it has a supercomputer. So that's why a lot of things we use the hand drawing on that. So you can see from this one, you can draw the graph with the annual return period. So the highest is 160 is here. You got data here. Then you can plot the graph. From this one, you will get equations. So by using the equation, you can use to predict for this one 10 years, 20 years, 30 years, 40 years, 50 years. For the 50 years return periods, what's the annual rainfall? Then you can plot on that. Or maybe use the formula for calculations. So you can see after you get this one, the data are arranged in descending orders and rank number assigned to the recorded events. The probability P of event is being equal to or exists in calculated by using Weibo formula. Calculations are shown in table 2.5. It may be noted that when two or more events have the same magnitude as for m equal to 13 and 14 in table 2.5, the probability P is calculated for the largest m value of the set. This return period T is calculated as T equal to 1 per P. A graph is plotted between the annual rainfall magnitude as the ordinance on arithmetic scale and return period T as a partial, maybe logarithmic scale. It can be seen that accepting the point of the lowest T, a straight line could represent the trend. So you got the straight line already, T equal to 10, then you can get T equal to 11.5. When T equal to 10, you can get the rainfall. And you can using the graph to get the informations. And if T equal to 50, this one we don't have the data for 50 years, 10, 20, 30, 40, 50, and you got the data of about 100 and 180. The return period of the annual rainfall of magnitude is equal to existing 100 cm by interpolating of 2.4 year existing probability equal to 1 divided for 0.174. And this example you can get from the engineering hydrology book as well on the books. You can look on that in more detail. One thing in Malaysia we normally use, actually those plotting the position is quite important for you to do the estimations. And for the design rainstorm, and mostly we use the graph, we call it IDF curve. In some of the places in UK, maybe we call it not call it IDF, they call it DDF. The total storm rainfall depth at a point for a given rainfall durations and ARI is a function of the local climate. Rainfall depth can be further processed and converted into rainfall intensity. Intensity equal to duration divided by intensity equal to depth divided by durations. Normally in Malaysia, we will use a mm per hour. So in 1 hour, how much the rainfall, the rain intensity, which are then present in IDF curve Such curves are particularly useful in stormwater drainage design because many computational procedures require rainfall input in the form of average rainfall intensity. The three variables, frequency, intensity, and durations, are all related to each other. The data are normally presented as curves displaying two of the variables such as intensity and durations for a range of frequency. These data are then used as input in most stormwater design processes. So you can see like IDF curve, intensity, you have got the rainfall intensity data, mm per hour, and D is mean the durations. The durations maybe like is 3 hours rainfall. Is 3 hours rainfall is about 72 hours. And there will have the frequency with various line. Normally like they have 2 years, 5 years, 10 years, 20 years, 50 years, and 100 years of the line. So from this, we use this IDF curve to design the urban drainage system. This one is more under like urban hydrology. I believe most of the students is the first time to enjoy the hydrology classes. Hydrology, like last time, sir share with you, like water have been used for a long time, so we have a lot of accumulated knowledge on that. One of the most important thing is try to have in our OBE learning, we have cognitive, psychomotor, and affective. Try to use your heart, use the affective to learn the hydrology, because you can see even the modern hydrology, we have about 500 years, close to 500 years. We have a lot of knowledge accumulated, and a lot of things is still using within the community. So you need to have the sense, engineering judgment. Sometimes like those Malaysians using the hydrology knowledge is different than those British, they're using the hydrology knowledge, and even the Americans and in China, they use different approach, because hydrology data is sometimes quite regional as well. But one thing is we will commonly use is, as an international standard, we use the IDF, intensity, duration, and frequency curve in our urban drainage design. And for this one, give you an example of the IDF curve. So this is the mass curve previously we shared before already on the rainfall or storm of total 270 minutes is about more than 1 day. 1 day is 24 hours, or it's less than 1 day. If 270 divided by 60 is about 270 divided by 60 is about 4.5 hours of the rainstorm. So you can see like for the first 30 minutes of the intervals, from 0 minutes to 30 minutes is accumulate 6 mm of the rainfall. After that, the second interval is accumulate 18 mm rainfall. If for the 90 minutes, it can be accumulated for the 21 mm of the rainfall. So for this data, you can see like, because this is the mass curve, is the cumulative rainfall. That means like for the interval of 30 minutes to 60 minutes, we add on about, the rainfall is about 18 minus 6 is 12, is it? For this period, in the 60 minutes to 90 minutes, the actual rainfall is 21 divided by 18. It's only 3 mm. So from this data, what you can do for, if you have this data, the mass curve rainfall data, what can you do in the IDF curve? You can draw the hydrograph of the storm at 30 minutes with time step, plot the maximum intensity, duration, and curve for this storm, and plot the maximum depth duration curve for the storm. This one is easy. Hydrograph, you just plot the things, 30 minutes, 60 minutes, 90 minutes, 120 minutes, 150, 180, and so on until 270. Just put on this one, the hydrograph of the storm. So you will see that the storm is the highest is at the 120 minutes because the intensity of the water is 30 mm per hour. You can use these methods to build up the maximum intensity and duration relations. You can see for the 0 minute, they got no cumulative rainfall, they got no rain in the 30 minutes. This one, when the first 30 minutes cumulative rainfall, the total rainfall is 6 mm. So all go for the first 30 minutes. And the 60 minutes, the cumulative on the 60 is 18. You can look back the data. On the 60 minutes, or in the total rainfall is 18 mm. So for these preparations, on the 16 you got 18. Then from the first 30 minutes, this one is 12. This one you minus this first 30 minutes because this is that's the number you get, and so on for the 90 minutes, and you got 21. 21 is this one, the number. 21 is a total, is a cumulative rainfall. Then you can trace back, and for this remaining is 18, this one is 15, and from this method you can go into entire calculations to build up this one, the incremental depth of the rainfall in various durations. And after we develop this curve, actually the purpose is when we're doing the design, we want to get the maximum rainfall at various times. So the maximum rainfall for 30 minutes, we found that all this data, the maximum is 15. After that, for the 60-minute durations is 22. 90 duration is 30, 37, 43, 49, 52, 53, and 54. Then all these bolded value will be used for the further design. So you can see maximum depth, because what we try to get is the maximum depth. Maximum depth is 15, 22, 30, 37, 43, 49, 52, 53, 54. So you can see this, the bold data. We want to get the maximum depth. That's the maximum depth. That's the durations. So that's the intensity. If this one, the maximum depth, we convert to the intensity, because this is the half hour. If in 1 hour, it should be times 2. So this should be become 30 mm per hour, 22, and so on. You can see the data. And you can plot this graph maximum intensity duration and maximum depth duration curve for the storm. This is the durations 0.270, and that's the maximum depth, and maximum intensity. So this one, the maximum depth is, you can see, will increasing. And this one is the maximum intensity durations. At the beginnings, the rain is quite heavy. After that, it becomes small and smaller. And that is the analysis and presentations of the. That's the analysis and the presentations of the data. And we look back on the PDF files. That's topic 2, frequency of probability analysis. And just now the two books Sir mentioned is Engineering Hydrology. This book. Again, show you again. That's the books. Some of them in details. You want to enjoy the study, please go ahead. And most important, you have to know how to do your tutorial. And another book, this one is Hydrology and Floodplain. This is a US book, and that's the book which Sir showed you before. So this one is talk about analyze the frequency and probability of the hydrological data. So always remember, like for this one, you can see we finished the CO1. CO1 is talk about like the hydrological cycle. So regarding how the rainfall in the stream, river, the surface runoff, we got the runoff coefficients, what's the percentage of that, evaporations, and the entire cycle. And the CO2 is when we have the rain gauge network and we collect a lot of data. So you can see all the questions, like the presentation we use, like just now the question we used 22 years of the data. So when there's the big amount of the data, this kind of data accumulation is being done for many years, like before the times of the computer. So you can see like some of them, they say, oh, the rainfall data is from 1932 or 1961. At the times, like computer is not yet very active. That's why you see the methods like we are using. Mostly we use the logarithmic graph, the skill on that to do the drawing, try to estimate the return periods using the probability and the frequency. That's why we have the frequency analysis and the probability. And another thing for sharing is this one is the MASMA second edition from DIT Malaysia. You can see like in their guideline, this is the chapter 2, quantity design fundamental 2. Chapter 2, quantity design fundamental 2. It's as mentioned in 2.2, rainfall estimations. Then this is the importance one, why you want to learn this thing. 2.21 average recurrent interval. Excuse me. Because in the Malaysia standard, we adopt of this knowledge on the rainfall estimation as well. You can see 2.1 average recurrent interval, that's the return period. When we're doing the quantity design in the urban drainage system, we need to consider at the beginnings, after we understand the hydrological system, the rain is fall down and all these things run off, and we have the data from the stations. we need to do the calculation, need to understand what is the return period and the time concentrations, how long the time is travel. Previously in the tutorial, we have a few examples. So we got the rainfall measurements on that, and after that we have the measurements on the river. In between, how the rainfall is flowing, the travel times, we not yet touch, but I think we will touch in the CO3. We will touch, we not yet discuss on that. This is a time of concentrations. At first, they want to know what's the return period. After that, they want to know the travel times, and they want to know the desired rainfall estimated. This is the IDF curve we mentioned, intensity, durations, and frequency curve, and the umbilical IDF curve, and the temporal pattern. So you can see like they use the same equation, TR equal to 1 to P time. Is this one will time 100 because they want to maybe do it in a percentage. Like this, the times of concentrations. The time of concentration is the travel time of the runoff flow from most hydrological remote point upstream in the contributing catchment area to the point under considerable downstream. You can see like in the tutorial 1, the question 1, I give you a catchment area. You got the rainfall this amount, and you got the measurement of the rainfall from the gas stations. You got the stream flow, meter cube per second at this amount. Then you try to convert to be the total volume of water, and you divide it by the stream flow to the rainfall. You got the surface runoff equations. But how fast like this rain is become the flow, the stream flow being measured, that's the times the runoff is need to travel. So that's the times of concentrations. That's the role of the civil engineer in the urban hydrology. We need to design the drainage, the sustainable urban drainage system. The concept of the times of the concentration is important in all methods of the peak flows estimation. It can be assumed that the rainfall occurring during the times of concentration is directly related to the peak flow rate. The practical is select during the storm duration as equal or greater than the times of concentrations. You can see it has a overland flow, the travel path, this curve, gutter flow, rain flow, because like some of the flow, when the rain will fall on the road, it's become the overland flow. Then you use different equation for the calculation. When you flow into the curves along the road, you use it's traveled at a different speed, and when it's go to the drain, become drain flow, it has a different speed. So this is the IDF curve. Just now Sir mentions the most common form of design rainfall data required for use of the peak discharge estimation is from relationship represented by the intensity, duration, and frequency IDF curve. The IDF can be derived from the historical rainfall data, and they are available for most geographical area in Malaysia. Recognizing that the rainfall data used to derive IDF are subject to some interpolation and smoothing, it desired the IDF curve directly from the local rain gauge record, and the records are sufficient long and reliable. So you can see this one, we have the IDF curve normally we use in the design. So there's a typical, just now so show the IDF curve. This one can show you again, which is in Malaysia, the DID, Department of Irrigation and Drainage, what they are using. You can see they have the curve, 2 years return periods, 10 years return periods, 50 years return periods. Of the 2 years, 5 years, 10 years, 20 years, 50 years, and 100 years. So it got 6 lines. You can see here, this is 2 years and going up. Then we will know from this, we will able to design the rainfall, whether we want to design for 5 years, 10 years, 50 years, or 100 years. For the different building, we have different requirements. Like in some of the residential area, maybe our design is only like 2 years or 5 years, or maybe in the main drainage system, maybe we need to design for up to the 50 or 100 years. It depends on the entire system. How do we do the flood roading? How do we try to drain off all the water from the rainfall down to the become surface runoff in the end, being drained out in the catchment area. And in appendix, this one maybe I can share with you in appendix. So that's the design standard. You can download and look on that. You just Google type the MSMA second editions DID Malaysia, then you will get the PDF file, because this is on copyright of the DID, so it's not maybe not good to sharing with the student. We have the permissions, but we can use on that. This is the standard we are using. You can easily download on Google. IDF curve for 5 minutes to 72 hours storm duration. So what we design is we use a 5-minute intervals to 72 hours storm durations. And this got weather stations. When you do the design, you can use the data here, because you got a stick of Johor. If you're in Johor, you use Johor, Kedah, Kelantan, Kuala Lumpur. You can see Kuala Lumpur, we got the station data we have. We have the Puchong Drop, we have the Ibu Pejabat main station of JPS. That's the station number 311603. And this station, another station, SK station, SK Taman Maruri, Edinburgh Kampung, Sungai Tua, SK Jenis Kebangsaan Kepong, Ibu Peak, KM16 in Kompak, Genting Krang, this one is Kompak as well, Kuala Seleh, Kampung Kedas Kompak, Air Terjun Sungai Batu, Genting Sempak. When you want to do the analysis, normally you can get the data from this curve. Surely you cannot get exactly the stations, because sometimes you use the interpolations, or maybe use the nearby data for the nearest stations. You can see like it has all the curve of the IDF curve for the storm durations for everything, and you can use in the design. So for the CO2, a lot of times like we want to do the frequency analysis and the probability analysis, because we accumulate a large amount of the data for many years. And at the times like when they're doing the hydrological analysis, it didn't have the computer at that time. So we come up a quite mature method like the IDF methods. We use the local thematic graph to do the drawing, and we have the 2 years, 5 years, 10 years, 20 years, 50 years, and 100 years return period on that. And when you do the designs, you can refer back this the IDF curve through the frequency analysis when you try to analyze the hydrological data. In the last lessons, I think I want to share you with one video for the infiltrations, and not yet sharing. I think I want to share this video with you because some of you may be interested and curious how the infiltration is being measured. This method is being developed also more than 100 years ago, so it's quite a mature way to do the things. Okay, I hope you enjoy the video sharing. So you can see like infiltration is one of the important elements, like we lost the water. Maybe through the infiltration process, the water will go down to the ground and become the groundwater again. So there's the methods like we are using the double ring we are using. We try to understand like the infiltration process. Then we try to do the measurements before the raining, and during the raining time we know how fast the water will infiltrate to moisture the soils and down to the bottoms. And this one is interesting. I want to share with you on another document from the Department of Irrigation and Drainage. This is a document for the review of the National Water Resources 2000 to 2050. That's the planning of the water. This is for Kuala Lumpur. This one, the Selangor, for this one we included the Kuala Lumpur and Putrajaya as well. You can see this is the stick area, 8,396 kilometers squared, and the rainfall is 2190 annually. Then the actual evaporation is 12,280 mm. So this is the annually evaporate. It will disappear through the evaporate, and this will infiltrate down to the ground. It's used the term groundwater recharge 150. Actually, it's not that much compared to the evaporations. It's only maybe close to the 10% only compared to evaporations. And the surface runoff will be a big portion, 760. That's become the surface runoff. You see the other stage, like the big stage, something like Perak, 21,000 square kilometer, and the rainfall 2480. And that's the infiltration rate and the surface runoff. Another big stage in Peninsular Malaysia, like the Pahang, got a very big land. The rainfall is about the same. It's quite close. 2470, and the actual evaporations also about the same. So that's why like this is quite important for you to do the frequency analysis for your data. Okay, now it's 5 o'clock already, and I hope you enjoy the class today. Do you have any short questions? And if later you have any questions, you can book my consultation times on Tuesday, 9 to 1 p.m. I'm stopped the recordings.